Please put your attendance in this chat box. Okay. So you see, in our last class, we already talked about how to take sample in sterile conditions, how to maintain sterility, how to sterilize the reactor. All those aspects we have completed, and then we also started discussing about the measurement. Okay, and today we will be focusing on more particularly for the measurement aspects. What are the different kinds of measurements we can have? I'll definitely share my screen so that you also know what are the textbook component we are discussing, and we also have some PowerPoint related to that. Okay, coming to textbook here, just for, so this chapter is, you can always keep in track so that you will not be misguided. This is about instrumentation and control. So basically, when we are talking about instrumentation and control, you need to know what are the things we are going to make measurement, how we are going to make control. Instrumentation and controls are totally two different things. For example, what is the difference if I simply speak in this class as I am talking here? So definitely we need to understand the difference also. So I'll just take few minute time when I'm discussing about these points. Measurement is, for example, measurement of temperature, right? You all know that when we are running a fermenter, maybe small scale or a medium scale or large scale fermenter, we have some temperature requirement, right? And in our last class, we also talked how much heat is generated, all those aspects we talked. That is fine. And if there is heat generation is there by your fermentation process means by metabolism, by aeration, those things you have already learned because I talked about those aspects. And now, so we know that we have to measure temperature. So temperature measurement is a very basic things we normally do. So measurement is fine. How we are going to measure? We are having temperature probe, right? I will talk about those things today. We have temperature probe. Different kinds are there. Mostly the temperature probe will be, we are using two different approaches that I'll talk very soon. And we are also temperature control. Control is actually governed by using the chilling, water flow control, right? So we are having a chiller through which the cold water, different temperature we can maintain, some 4 degree to 10 degree cold water, we are passing through the fermenter, right? So control is purpose is to allow the maintenance of what you want, that is called control. So water will flow in the jacket so that you can maintain the temperature. So control is for establishing whatever is required, and measure is whatever value is there to know. So knowing one thing, controlling another thing. In most of the cases, measurement and control are always coupled. So temperature will be measured, it will be going to controller, controller will try to fit this temperature gap PID controller, and they will activate the chilling water pump. So these controls are actually going to be governed by how we are going to manage. So strategy may differ. So for example, pH measurement and pH control. pH measurement is done by pH meter. pH control is being done by two peristaltic pumps connected with the drive. So the pump is going to control the flow of acid or base. So control are different, measurement is different. Same way, dissolved oxygen is there. But anyway, dissolved oxygen do not have any controller for that, but we can only measure. So some parameter will be only measuring, like dissolved oxygen, we will normally measure, not really control. Okay. But we have possibility of controlling, that is for flow rate. Airflow we can increase or decrease. So there is also a valve device. So compressed air is coming now. So this is a gated valve which can be actually controlled by the controller also. So if the oxygen concentration is too high, it may stop. So these controllers are there, but not widely used for fermentation process. So our objective in this class, what we are going to learn, maybe today and next day, we're going to learn about control. What we are going to control is temperature measurement and control, possibly. Dissolved oxygen will be going to measure and control. And similarly, pressure, measure and control. These are the primary things we will be going to focus in this class. We'll be talking about some design and dimension also, but not in mechanical details, as biotic details will be definitely going into their component. Now, okay, these are the things we are going to learn. Now, I'll show the textbook component here. What are the different kinds of sensor, controller is there. So when we are talking about some sensor, that means it is going to measure something. Okay, measuring element, that is called sensor. It is going to measure either temperature, either measuring pH. So we need to have there, but always it need not be going into that. So sometime we may measure dissolved oxygen without going into liquid phase. Similarly, measuring carbon dioxide is actually coming out, right? So if I am measuring what is the gas coming out, we can actually measure what is the carbon dioxide concentration in the reactor. So some measurements need the probe should come inside the liquid. Some measurements can be done without the probe coming into liquid. So it is upside, top. For example, it is measuring pressure. To measure pressure of a fermenter, we need not have any pressure gauge which is connected to the liquid, not needed. So we can measure it from exhaust pressure, whatever pressure is built up in the fermenter. So some of those things you can actually go and see. Some sensor is actually coming inside of that. So like pH, dissolved oxygen, they will go and go inside the liquid phase to measure, because most of the property like pH, dissolved oxygen are property of liquid phase compositions or measurement. Some will be there which is outside, like exhaust gas. We are having measurement for electrochemical sensors also, and pressure transducer for carbon dioxide measurement and oxygen measurement we can normally have. So that is not only for carbon dioxide. We will also have some infrared measuring device for carbon dioxide and oxygen. What they do, the principle I will talk you later.
Excuse me, sir.
Yes, my screen is shared.
Sir, your screen is there. One of my friend is waiting outside, sir. Can you please admit him?
Okay.
Thank you, sir.
So we are talking about different kind, right? So one of the kind can go inside. That means the sensor. Sensor means the element which is going to measure. So in most of the time, your pH probe will come inside the liquid. Your dissolved oxygen probe, dissolved oxygen probe will come inside. Foam will be top, it will not come. Anti-foam measuring or foam measurement. Similarly, pressure transducer, it will never come. We may have simply a pressure gauge. Now, exhaust gas, right? Exhaust gas, when coming out, we can pass this gas through IR measuring device, infrared measurement for oxygen and carbon dioxide. If you want. So 2 IR tunnel is passing and we can measure. We can also have a flow meter. Flow meter is normally done for input gas, which is coming here. That can pass through a flow meter. That is flow measurement for your gas. So air bubble is coming. So this is a flow meter for your air supply. This is for exhaust gas. There are many other methods for exhaust gas measurement. These are actually inline, okay? And these measurements we are going to measure directly pH or DO, these things. So basically, and temperature probe also, it will come inside. So temperature, DO, temperature, pH can be, these things can be monitored and controlled also. This exhaust gas is actually measuring, okay, what is this? Principle I will talk to you later. Basically what is happening here, carbon dioxide is actually causing change in resistance in a filament. So here what is happening, we can have a filament and filament is causing, for example, some light source and radiation it is producing. And here is one, we are measuring the light coming into the receiving end. And if the gas is flowing through, they will actually deflect. Try to understand the principle. So any light source visible, it is not actually visible light, it is actually infrared light, in case of carbon dioxide measurement particularly. So what the principle? We are having infrared light source, and here we are having the infrared receiver, and in between them the carbon dioxide or oxygen, whatever gas is passing. Depending on concentration of carbon dioxide, the deflection of the IR can happen. And what is it is measuring? It is measuring how much of light is falling on the receiving plate. Okay, so this is actually photoelectric devices, or they can actually amplify how much signal is there, and based on that you can actually measure carbon dioxide concentration in a gas phase. So this is actually inline measurement. Directly we can do all those analysis possible. Now these are the kind which is called actually inline measurement we normally have in our system. Some of these things can actually be online. That means you can have a control and you can see here. Inline is sensor that is integrated part of the fermentation equipment, and measured value obtained is directly, okay, in the process control. It is part, okay, that is inline. So when I'm going to have this exhaust gas connection, we can go for that. Online means although sensor is integral part, but the measured value cannot be directly for control. You cannot really have everything in your hand. Offline is totally separate. We can put it together. Sometime we can also going for measurement of separate entities, separate other properties. So inline is on the fermentation board itself. Online is with time, same time we are going to measure. Okay, and if you have some control into here, operator must enter the measured value into the control system if the data is to be used for process control. So I need to tell those values. Offline is actually outside. We are going to measure some cell dry weight. We are going to measure some glucose concentration in your fermentation media. If these kinds of approach are there, these are going to be offline measurement, or offline sensor can be utilized. So basically these are the sensor components. And first thing you will be measuring is temperature. The most widely is thermostat we will be using. So thermostat, what does it mean? So thermocouple thermostats we can use. So basically the thermometer itself is containing a thermocouple, And depending on temperature, when I'm going to have a thermocouple, the conductivity of the material will change. So if I am having some thermocouple inserted in our fermentation broth, and as the media is getting hot or cold, the conductivity of this material will change. Okay, so essentially we are actually measuring, we are already putting a voltage input is there into your probe, and it is going to measure the change in volt across the element. So basically we can actually measure the change in temperature by this process. Same thing is also happen here. For example, they're taking some platinum wire, they are going to measure the resistance. Okay, and whatever, so the wire resistance will change. So as the temperature changing, resistance change. So we have to do a calibration outside. What does it mean? We mean that we will do the same device we are putting in a fermenter, and we will change the temperature, for example. And I know if I change the temperature as 40 degree, I'm getting this much of voltage difference between the wire end. So that means I will note down, this is the temperature, this is the voltage change. So basically, each instrument and every instrumentation panel is to be calibrated before we are going to use. But by principle, we can have these kinds of approaches for temperature measurement. Okay, we do not use actually the glass thermometer, right? Many of you already have seen glass thermometer for temperature measurement, mercury. But that is not really accepted in fermentation. The reason is very simple. Many times the glass thermometer will break off because your fermentation agitation is going on, right? There are so much movable things, and glass is fragile. So glass temperature measurement is only done if you are going to do in very small scale without much agitation. You can use. Otherwise, most of the measurement devices thermocouple we can use. They are really very accurate, particularly when you are going to use an industrial process. So we will be talking about those thermistor. Okay, thermistor is actually going to measure the temperature. What is the function of resistance in temperature? So there is like rheostat you have studied maybe in your class 2. So resistance. So coil is there. We are actually changing the coil length. So the resistance of the material is changing. Thermistor is also will be working in the same principle to measure how much temperature gap is coming up in this process. It is really cheap and it can have measurement, but sometime when the resistance is increased proportion to high level, then maybe temperature change and resistance are non-linear. So some problem can be there associated with these kind of thermostats when you are going to use in online temperature monitoring and control devices. So basically, these things you need to understand when you are going for temperature measurement. And what about the control? Control is really not difficult. It is really straightforward, because control will be always using some liquid coolant passing. Mostly water will pass through the jacketed vessel. If you think, or if someone thinks that fermenter is bigger size, bigger dimension, we can have the cooling coil. And if high temperature removal is required, then we can also use, I mean to say, this one, brine. Sometimes we can also use brine solution. Brine is having more capacity to absorb heat from the liquid. So instead of water, we can use brine, because you know brine is normally having higher boiling point, so it can take up more time, it can operate. So mostly the temperature measuring device or pH measuring device need to work for longer period of time. So temperature control in these things, you need to have a very precise measurement. They can change it very rapidly. Flow rate, a basal flow rate is always maintained. You try to understand why? Because for example, your fermenter you are starting at 25 degree. Of course, room temperature is 25 degree. So do you think there is no need to put any water? Yes, it is still required. The reason is that the fermentation media, if it goes 30 degree, for example, your water flow rate cannot really bring down the temperature within second or minute. Sometime it can take some hour also. So please, when you understand that when you are talking about any fermentation process and you are passing some cooling liquid, the temperature change is not instantaneous. Okay, temperature change is not instantaneous. So we need to have always a temperature control liquid flow at basal level. So for example, I need 25, so always some 25 will go. If there is atmospheric some change, then temperature will bring down. So cooling liquid temperature they maintain, and it is not as per requirement, but it is a continuous flow is generally inducted in a large scale fermenter or bioreactor process. So these things you will do. Okay. So in some cases, it may be better to run the cooling water continuously at some steady rate, because otherwise you cannot really have a control very effectively. So these things is there. There may be some provision for circulation of refrigerated brine. So this is done, but you should be very careful. The temperature control is not as fast as we have for other devices. So this is for temperature measurement. Now, once the temperature measurement is done, the next topic we will be discussing is flow measurement. Flow measurement is for two types. One is for liquid and another is for gas phase. So when I am talking about flow meter, basically we are talking about the gas flow meter. These kind of flow meter as thermal mass flow meter, these are non-specific. I told you that infrared gas measurement is also there for carbon dioxide. Okay, we have used them. Very small device. It is very easy to use also, not a difficult one. But that is some requirement is that it is only specific for certain gases. Every gas cannot be measured. You cannot measure nitrogen there. Okay, because they are not calibrated, right? Your instruments should be calibrated. Now, there is some measuring devices will be there which is non-specific. Any gas coming, it is just flow rate will be measured, and one of them is widely used this thermal mass flow meter. How do they do that? The principle is simple enough. Basically, in this process, you can see also the diagram, or maybe I'll go into your PPT also. One PPT is there. Maybe next class we'll go. So essentially what is happening, there is some thermistor here. So we are going to measure the temperature at starting and end, and we are also having some element, okay, measuring the heating elements, meter to measure the power. Now what is happening, how they are going to do this? They are going to do this because we know the heat transfer, for example, H U into Cp T2 minus T1, right? So heat transfer in any process depends on temperature difference, specific heat, and how much liquid is flowing through or gas is flowing through. So you see, I know the temperature here because I am measuring. I know the temperature here, and here some heating element is there. So what will happen? The flow of air is going to conduct, it is being heated, right? So T1 temperature is becoming T2 temperature. How is it becoming? Because the gas is flowing. So if the gas flow rate, if I know, for example, this much kg per minute, that means I know how much heat is being lost, right? So I can measure the power requirement here. If I know how much power is there, and if we can measure the temperature between them. So H is known, heat transferred. Q I don't know. Cp is the specific heat. So for example, we are passing air and we know specific heat of air, this much kilojoule or joule, okay, per kg. These are known. Temperature T1 and T2 are monitored. So through temperature and your power consumption, that is the meter to measure the power, you can actually calculate the flow rate. These flow rate measurements are fairly accurate, but you can have some differences. Maybe in cases some 5% or 10% flow measurement can be varied. This kind of flow measurement is only for, I mean to say, for gas phase. Definitely not for liquid phase. Liquid phase, there are actually bureting devices we can have, so we can actually measure how much liquid is passing through it. We can also have liquid flow rate can be controlled by peristaltic pump. I think There is no diagram for that, but I'll just let you know how we can measure the liquid flow rate. Gas flow rate you understood, right? Temperature, temperature 1, temperature 2, and I know how much heating element cost is there, means how much power is consumed. And this is the air is flowing, or maybe some gas is flowing. So gas is being hot, right? So it is taking out the temperature from being hotter here and reaching. So temperature, this one T1 material is becoming T2. How? By taking the heat, right? So that's why they are doing Q is known, Cp is known, temperature difference is known. So if I know flow rate, if I know specific heat, if I know the temperature gap, I can calculate how much heat. So Q is H by Cp delta T. I measure the temperature, I know Cp, I know H, flow rate is fine. In case of liquid, it is not like that. It is having some difficulty, particularly for liquid flow measurement. One liquid flow measurement can be through, first one approach is that we can have some flow meter. Okay, maybe we can use orifice meter or rotameter. Rotameter is also used for gas also, but some 5% variation is there. So what is rotameter? I think for your batch, we have not done any lab in our biotech, but otherwise in some coming semester, you will also learn about the rotameter. Is the simplest one for measuring fluid flow rate of liquid or gas. Design is very, very simple. Now, how does this rotameter works? If we want to know the liquid flow rate, very simple one. Let me see. This is, for example, one glass connector. You see, I'll just show you. This is a glass chamber, right? Okay, glass or Pyrex glass, whatever you want. And there is a one big lightweight, not very heavyweight, one cone or ball is there. Essentially cone. Now, if the liquid is coming at some force, it will push this ball to float. It will float out, right? Otherwise, the ball is sitting in this bottom side. Now, liquid is starting means it will flow. So it will float. If you increase flow rate, then it will go and touch here. But it is a spherical ball. It is not that completely locking, right? It is not stopping the liquid to flow. It is allowing the liquid. So ball will be not completely locking, but it will allow the liquid to flow through surrounding it. So for example, this is the ball. So liquid is passing through and finally going out. This, how much the ball is rising because of the flow, how much height, there is a scale. And that is actually rotameter. So ball is floating. It can be, mostly it is actually metallic ball. And when we are having the flow of liquid or gas, depending on what flow rate you are maintaining, the ball weight can be controlled. Light or heavy, diameter can be changed. So essentially it is the simplest one. You see, I don't need anything. But we need to calibration because I have to pass some flow rate and I will measure, okay, it is floating now 2 centimeter. If I pass the liquid at 4 meter cube per second, for example, it is coming 6 centimeter height. So I can have a calibration. Then I'll put a scale on the rotameter. This is the simplest one, flow measurement device. The second one, I think you understand, right, what I'm speaking. Second one is actually pump. Peristaltic pump. Peristaltic pump is actually discontinuous pump. What is it? Basically, this is one flexible pipe of silicone. Silicone pipe, probably you have seen. They are mostly used for liquid flow in lab. And here is a gearing device. two gearing device. So these gearing devices are rotating, for example, not very high speed. This is the peristaltic pump unit, for example. That means I am passing the tube or pipe through which flow is going to take place. I want to measure them. So this is actually peristaltic pump. Why peristaltic? Because this will rotate. And as it is rotating, the liquid here is not, they will be passed. So it is actually causing squeezing. It is causing a pressure, and as it is rotating, the liquid at the back side will be drawn and it will be pumped through front side. And we can have a controller here, flow rate controller. So for example, I'm going to control flow rate of 3 liter per minute or something like that. So as we are making a control of what is the flow rate, the rate of this rotation speed will also be controlled. So flow rate, it is not a measurement, it is rather control devices which can actually go for delivering liquid in fermentation process, bioreactor process. You understand why it is called peristaltic? Because peristalsis means it is a discontinuous rhythm, it is not a continuous one. So essentially whatever I am showing here, you may see that I am showing a round ball. Actually it is not like that. It is actually mix up of 3 connected ring. So continuously it is not pressing. One side it is pressing, then the next connector head will come, then it will press. So discontinuous pressing is going on. And peristaltic pump is widely used for delivering acid, base, and for example, antifoaming agents delivery, they are widely used in bioreactor system. So this is the basic design of peristaltic pump. This is the last slide I talked about, basic design of rotameter as a flow meter system. So these can be utilized when you are going for a fermentation in liquid flow control. These are the basic configuration we can have. But we can also have, in some cases, for example, here, we can also have a magnetic coil driven flow. So actually they are causing induction. So if the fluid means it is not definitely water, right? It is some conductive material. So if the conductive material is flowing through a magnetic, around a magnetic coil, what will happen? Electricity will be generated, you know, right? So this is the theory of induction. So it can also be magnetic flow meter will actually cause the measurement how much potential is generated because of the flow of the liquid. If I know the liquid characteristics, you know this is a conductive liquid. Most of the fermentation broth are actually conductive because they are filled with different kinds of salt and nutrient. It is very likely we can have electricity will be generated in the outer coil. So magnetic field is going to produce electricity over there, and we can also measure. But they are very costly, though they can actually be very accurate for measurement. And what is the other advantage? There is no much pressure drop in these kinds of conducting elements, which are actually non-invasive. You are not really stopping the liquid, but you are still measuring the conductivity of the flow, how much liquid is passing through the unit system. Are you getting this point? So it is actually indirect method for flow measurement can be done. We can have different kind of peristaltic pump or piston pump you can use. That is fine and easy to measure actually. Actually some balance or load cells are also there. Balance and load cell I think is not widely available, but it is also there. What is that? I just talk about. Load cell is also used in case of few fermentation process, not everyone. Basically, a load cell is nothing like a balance only. So basically, for example, this is a platform and there is a small rack for each of your bottles. So on this rack, you are putting your, for example, media bottle, okay, or some sulfuric acid, nitric acid, whatever maybe. Now, as you are taking out or pumping out something, what will happen? The weight, what it is measuring, it is pressuring. So the weight will reduce, and this weight measurement is going to controller. What does it mean? It means that how much liquid has been discharged or delivered from this can be measured. And based on this input, for example, it is measuring the weight. So it knows that after 5 minutes, this much of weight is lost. So essentially, it can actually give you the idea what is the flow rate for this. So pump is already running to pump it out, liquid into fermentation broth. But we can also have a weight measurement devices online, which can directly measure, you need not do anything. So total weight is known. And as the weight is lost, we can calculate the weight loss. And this weight loss information is transmitted by transducer to the controller. Controller decide, okay, this much weight was there. After this time, this is the change in weight. And if we give the specific specific weight information of the media, then we can really calculate what could be the possible flow rate of these kinds of liquid. So liquid flow rate measurement is really not so difficult. Now, next unit is for pressure. I should tell you, pressure measurement is not really very common in fermentation industry or bioprocess system. Very few industries and bioprocess system actually include the measurement of pressure. Why? Because the measurement of pressure, most of the fermentation process and biological reaction is not much dependent on pressure. Okay, but sometime we need. What is the reason when we need? We need for those fermentation process where there is a generation, particularly anaerobic, where there is a high amount of gas formation, for example, carbon dioxide or methane is produced. And if we don't know how much pressure is there, we will not collect it also, right? If I see high pressure, then I will open the tap and I will collect the gas. If I do not measure it, we cannot have any control on this. This is the first reason. Second reason is that when we are going to have a fermentation process, we need to have some over pressure. Normally, more than 1 atmospheric pressure is maintained in the fermentation. The reason is that if the fermenter is over pressure, what will happen? No air can come in, but air can go out. So what does it mean? It means that there is a very less chance that outside any microorganism will come inside the reactor. So contamination chance is really reduced if we can, by some way, if we can maintain the pressure in the system of a bioreactor or fermenter. The most one widely used is pressure gauge. Pressure gauge is very simple principle. It is a mechanical gauge. So it is one connecting tube is there. So as the pressure of the gas is increasing, it is pushing a piston or rod pinion. Okay, it is some spring loaded rod and pinions are there. Basically, I'll try to show you most of the pressure gauge design. It is really simple. You need not really worry much on that, just for understanding. So what is there? It is actually one measuring rod. Here we are having a crank. It is pushing down. Na? So here one meter is there. Here it is centralized position is, so that means it is pivoted here. And now this device is having a spring. So for example, this flanges and some springs are loaded here. And this is being connected with a fermenter, for example. So what will happen? This is closed, of course. Now pressure is built up, right? So air or gas is building up. So it will push. Here spring is there. So it is increasing pressure will push the rod. And as the rod is pushing, it is connected with the meter, right? Dial. So it will actually push. Of course, spring device is there. So it will change the dialing. So increasing pressure is actually mechanical transmission of the pressure into spring. That is actually pressure gauge. Pressure gauge is used most of the time. Some other devices is also shown in your textbook. That is, one is the diaphragm measurement. Diaphragm is actually no pressure, no direct contact with the liquid, but diaphragm will try to put a barrier between the liquid phase and the gas phase, so that we can actually maintain the pressure or maybe sterility, because here is a problem. problem is that you see there is a possibility that there is some leakage of gases, all that. But if I'm using some diaphragm membrane, diaphragm is not a direct one. So we are pressurizing some, for example, here the pressure load is coming. Here diaphragm membrane is there. And we are measuring the pressure gauge or output at here. We can do. So pressure is being transmitted over a membrane, like where pressure is being created here. So it will push down membrane little bit. And that will cause this air to compress. And this will release the measuring devices here. One elliptical spring is there. So basic design I will speak in next class, not today. I think it's fine. You can speak in the next other day. And I will also show you. You see the same design as I am telling, diaphragm type. We are pressurizing somewhere, the same pressure is being transmitted and we are putting. So anyway, diagram, this looks good as I have shown you. So pressure measuring devices can be the Bourdon tube. Bourdon tube already I told, it is very similar as I have shown you the pressure gauge. It is a metallic tube which is rotating. I showed you a linear one, but you can have a metallic tubes of some elliptical nature. The tube is actually round, but as pressure increases, it will be a little bit squared shape. And that will actually push it. Pushing it, the needle is there, pinion needle is there, which will give you the reading. So basic principle is like that. I'll stop this discussion right now here. I hope you understood, right? Some of these principles we discussed in this class. Do you understand? Student?